History.
This is 1981 Mechanic C. Question 3. A thin uniform rod of mass m1 and length L is initially at rest on a frictionless horizontal surface. The moment of inertia of the rod about its center of mass is m1 L squared divided by 12 as shown in figure 1. The rod is struck at point P by a mass m2 whose initial velocity v is perpendicular to the rod. After the collision, mass m2 has a velocity of minus 1/2 v as shown in figure 2. Assume the following in terms of, answer the following in terms of symbols given. All right. So the thing hits, bounces off, and the thing goes and looks like it's rotating. All right. Why don't we do a little analysis of this? Just what physics could we use in this problem? For instance, let's see. Could we use Newton's second law? Does Newton's second law apply to the collision? Well, does it? You tell me. Does Newton's second law apply to this collision? Well, the only really circumstance where Newton's second law doesn't apply would be in a non-inertial reference frame. And this certainly is an inertial reference frame. So Newton's second law we could use that. I don't think we have enough information for it to be useful. But certainly we could use Newton's second law if it applied. All right, well, the next one is conservation of energy. Is energy conserved in this collision? And of course, energy is always conserved. But the real question is mechanical energy conserved? And it's possible, right? This could have been an elastic collision. I see the ball bounces off. But it's unlikely that this was a completely elastic collision. So I wouldn't count on being able to use conservation of mechanical energy in this problem. Let's see, what else do we have? How about conservation of momentum? Is momentum conserved in this collision? Well, is it an isolated system? Let's see. Viewed from above, it's on a frictionless surface. If we got the rod and the mass, or the ball, whatever that thing is, that's our system. Yeah, there's no outside forces, no unbalanced forces. I mean, gravity's pulling it down and the normal force is pushing it up, but there's no friction. So, momentum is conserved. Is angular momentum conserved? Let's see, is there a net torque on the system? Well, there are no net forces, so there can't be a net torque. All right, so angular momentum is conserved. And what else do we have? Let's see. And we also could use Newton's second law for rotation. I'm sure that's valid too. Because there is no, let's see, sure. All right, so these are all on the table for us. The only thing that we've eliminated is the conservation of mechanical energy, so we can't use that. All right, so we should always know what we can use and what we can't use going in. Don't just answer the question, because in the end you're going to need to know all that stuff too. A, using the principle of conservation of linear momentum. Oh, okay, well, it's conserved, so that's good. Determine the velocity v prime of the center of mass of this rod after the collision. All right, let's see what we got here. So we got a rod like this. I'm going to set up a coordinate system, I think. So this is M2 and V, and I think I'm going to set up a coordinate system right about the center. Everything's going to happen around the center. So I'm going to set this sucker up like that. There's going to be my x-axis. There's my y-axis. Probably the top's going off, but that's okay. There's nothing interesting going on up there. Don't worry about up there. Nothing to see up there. All right. So there's my y-axis. Here's my x-axis. And this thing's going to hit Boop, 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 boop. They said that was L over 6, really, but what I want to know is, what's this position? This is going to be negative, what do we got? So this is going to be, this point where it hits is going to be negative 2L over 6 in my coordinate system, which of course is minus L over 3. Determine the velocity v of the center of mass after the collision. All right, well, then we have this after drawing. This was before, and this will be after. So this thing's going to start rotating about its center of mass. It moved. Here's X. Initial Y was here. Somewhere on there. And then this thing bounced off on that same line, only now it's bouncing off at V over 2 that way, right? And this goes with a velocity V prime. Calling that V prime. All right. Using the principle of conservation of linear momentum. All right, well, that's kind of, I think this is going to be pretty straightforward. P0 equals P1. And so initially we just have M2V equal, I need a better marker than this. M2 negative V over 2 plus M1 V prime, right? That was M1. I didn't label that. That's M1 right there. All right, so what do we have? 3 halves M2V equals M1V prime, or 3 halves M2 over M1V equals V prime. All right, I think that's it. That was pretty straightforward, actually. So for A, I wonder if I'm off the board. I don't know. We'll see. I'm not off the computers. I'm not off the video screen, but by the time it makes it to YouTube, that might be off. I don't know. Well, we'll find out. Keep in mind, even if something's rotating or whatever, momentum of the center of mass of these objects will always be conserved as long as it's an isolated system. It doesn't matter if it's spinning or not. And Newton's second law also applies. Even if we're using the rotational version, the linear version also works as long as it's an inertial reference frame. B, using the principle of conservation of angular momentum. All right. Determine the angular velocity of the rod about its center after the collision. All right. So we're going to say the angular momentum about the center, about my my origin in my coordinate system. How convenient. To the origin of my coordinate system. This has an angular momentum right here, which is going to be R cross P. R cross P. I guess I'll call that P2. And I'll call that 2. Right? So the angular momentum here is due to, we got our position vector, R cross, and sense of velocity is this way, P. But I think I'm just gonna find the moment arm, right? We got the moment arm right there, right? There's our perpendicular right there. So I'm actually to find this, I'm actually just gonna say R perpendicular of 2. This will give me the magnitude times P2, right? A little scalar operation there. This is going to cause this thing to rotate. So our angular momentum is going to be that way. So that's the direction. Let's just calculate our magnitudes right now. This is going to equal, now in this case, we are going to have the angular momentum of this and that. Now this one, again, it's a particle. We're going to, it's not a particle, but it's just a blob, a small object moving. So we're also going to go, R cross P 2 of 2, and I will call this primes. This is afterwards. We'll put primes on there. I'm just saying 2 to identify that as that thing, the ball, And plus, we got to add to it the angular momentum of this thing, which in this case, we got this thing rotating about its center of mass. We're going to use I omega. I omega, right? All right, and we know that. We want to know that. We know that. We can figure that out pretty easily. And that's just going to be r perpendicular 2 prime times p2 prime plus I, which is, well, I'll just say I omega for now. You could say I omega. And we know how it's going to be rotating. It's going to be rotating. It's going to have its omega is going to be out of the board. So we know the direction of this thing. That's going to be pretty straightforward. So our perpendicular is L over 3. L over 3 is our perpendicular from the center of mass times m2 v equals L over 3 times negative, oops, let me put the negative inside, negative m2v over 2. All right, that's pretty sloppy. I think I'll clean that up. Plus moment of inertia, which is m1l squared over 12 omega. All right, so I just got have a little algebra to do. That should be pretty straightforward. L3 m2v plus lm2v over 6. Here we go. m1l squared over 12 omega. All right. Having some marker issues. Let's see, that's 2L over 6, so that's 3L over 6, which is L over 2, M2V L over 2, right? We got 3L over 6, yeah, okay, times 12, M1L squared equals omega, M goes away, and that becomes a 6, and that becomes a 1. All right, so there we go. There we go. That's B. All right, now I got to erase. Determine the change in kinetic energy of the system resulting from the collision. Well, I guess that confirms that mechanical energy is not conserved unless the change in kinetic energy is 0. Let's see what we have here. All right, to find the change in kinetic energy, I'm just going to find the kinetic energy initially is just 1/2 m2 v squared. So we need to find the kinetic energy afterwards. That's going to take a little work, I think. So K2 afterwards is going to equal, I'm going to call this K prime, just because I'm using 2 for the mass here, is going to equal K of 2 plus K of 1. Now, K1 has 2 parts to it. It's translating and it's rotating like that, like a little baton twirling around in your fingers. It's rotating. So this is going to equal, this is going to have 2 parts. This is going to have K rot plus K trans. Right, so that's going to have 2 parts to it. So I'm going to actually have 3 pieces to this. Got to make sure I do that. You got to look at that thing. Go, oh, it's got a linear momentum and a linear energy and it has a translational energy and a rotational energy. This only has translation. So this is going to be 1/2 m2 v over 2 squared. The fact that it's negative is not important because energy is a scalar. All right, plus, let's go with K rot first. That's going to be 1/2 I omega squared afterwards plus, and that's after, right? And then that's going to be around the center, and K trans is going to be 1/2 m2 v prime squared. All right. And we have all those things, so it looks like we have a little bit of algebra for us to do. But actually, if we've spelled that out, we're in good shape, even if we couldn't do the algebra correctly. So what do you got? 1/2 m2 v squared over 4. Should add a parentheses around that. Plus 1/2 m1 L squared over 12. Omega prime, which is that, which is 6 m2 over m1 L v squared, right? Plus 1/2 m2 times 3/2 m2 over m1 v squared. Right? All right, that's good. That's going to be some messy algebra. I could see this is just all set up for mistakes. 1/8 m2 v squared plus, what do we got here? m1 L squared over 24 times 36 m2 squared m1 squared L squared v squared. All right. Plus 1/2 m2 times, what do we got? 9/4 m2 squared m1 v squared. All right. Oh, the v squared. Wait a second. That should have been. That's not an m2. That's an m1. That's m1. I keep thinking that's 2. That's 1 right there. That's an m1. That's an m1. 1/8 m2 v squared plus 6 times 6 is 36, and 6 times 4 is 24. So we got m2 squared over m1 v squared plus, let's see, this m1 can go away with that. What do we got? 9/8 m2 squared v squared all over m1. Got 1/8 m2 v squared plus, looks like we can combine these. That's 12/8 plus 9 is 21/8. 21/8 m2 squared divided by m1 v squared. All right, well, that's kind of a mess. That's K afterwards. That was a lot of work, a lot of just algebra. All right, we're not done. We still find delta K. We got to subtract these two things. All right, we got delta K, which is going to equal K afterwards minus K, which is going to equal, oh, this mess, m2 v squared over 8 plus 21/8 m2 squared over m1 v squared minus the initial kinetic energy, which was just 1/2 m2 v squared. All right. So I guess we're just going to subtract these two things. So we got 1/8 minus 1/2. So that's 4/8. 1/8 minus 3/8. Negative 3/8. So what I got? 21/8 m2 squared over m1 v squared minus 3/8 m2 v squared. That looks like that's the change in kinetic energy right there. All right, so that would be C. I guess we could factor out the v squared and one of the m2s if we wanted to. But I think that's the answer. Delta K, 21/8 m2 squared over m1 v squared minus 3/8 m2. That's a lot of algebra. Not a lot of physics in there, but some algebra. You need to be careful here. You need to look at this thing and say, okay, we only have translational kinetic energy. Here we have translational plus. It's rotating about, it's going this way. Doing one of those things. It's spinning. All right. I'll see you on the next problem.
History. Physics.